So now we're going to talk about another law which deals with gaseous mixtures. So before, we were assuming that we were dealing with only one gas in different situations. So all the problems that we were discussing talked about basically the laws applying to one gas, excepting, of course, where there's a reaction that is taking place. Now, in this particular case, we're talking about a situation where there's no reaction taking place between the gases, and we're looking at, some relationships between, different properties of gases like pressure, volume, and so on. So this is what Dalton's law of partial pressures is all about. It says that basically, when you have a mixture of gases, the total pressure of that mixture is equal to the sum of the partial pressures exerted by the separate gases. All right? So simply put, if you want to express it mathematically, we can express it this way. P total is equal to P1 plus P2 plus P3 plus, the rest, all right? Whatever the number of gases present. So basically what this is saying is that if you have the individual gases present in a mixture and each gas exerts their own pressure, then the total pressure of that gaseous mixture will be the sum of the individual partial pressures of the gases, of each gas. And when we're talking about the partial pressure of a gas, we're talking about the pressure exerted by that gas as if it were alone in the container. So therefore, we can write down individual expressions for pressures based on the ideal gas equation for each gas. So this is the expression for gas 1, this is the expression for the pressure for gas 2, and so on and so forth. And some interesting situations can arise out of this, which I'm going to examine right here. So let me choose my ink. So basically, as we said before, P total would be equal to P1. Messing up already. Let me erase this here and go back to my black ink. Okay, so P1 plus P2 plus P3 plus all the way to the nth gas, Pn. All right? So if we substitute, now remember, P for each gas will be equal to nRT over V, right? So if we plug into this equation separate individual expressions of nRT over V, then we will get the following. Now, basically, the only difference between the gases would be the pressures and the number of moles. The temperature would be the same, and the volume would be the same because they're all in the same container. So therefore, for P1, the expression we would write for that would be N1 RT over V. And then for P2, it would be N2 RT over V. And for the third gas, N3 RT over V. And that continues to the nth gas, NNRT over V. All right? And we can simplify this a bit by factoring out RT over V, and we'll end up with N1 plus N2 plus N3 plus continuing to NN. All of that multiplied by RT over V. So this part here, within the parentheses in this expression, would represent the sum of the number of moles of all the gases in the mixture. So we can simply represent that as NT, T for total, and therefore that reduces this equation to NT RT over V. So this would be equal to the total pressure, PT. So what this is telling you is that the total pressure of a mixture of gases would be equal to the total number of moles of all the gases times R times T, divided by V. All right? So that basically is the result of Dalton's law of partial pressures. All right? And the next slide, well, not the next slide, the other slide, this slide right here, shows you the relationship in terms of actual values, numbers associated with the different terms. So what we have here are two containers. Firstly, one container containing hydrogen, it gives the moles and it gives the pressure. And then this container contains helium, that's a moles, and that's the pressure of that particular gas. And the volume and temperatures are the same in each case, right? So if we mix these two gases together in the same container, what you'll find is that the pressure will be additive. In other words, the total pressure will be equal to the pressure of helium plus the pressure of hydrogen, right? Again, given that the volume and the temperature would be the same for all the gases. So that's basically what Dalton's law is saying, right? That the total pressure of the gaseous mixture will be equal to the sum of the individual partial pressures of the gases that make up the mixture. And here we see the number of moles being added up as well, right? And in this case here, we had 0.60 moles of hydrogen. Here we had 1.50 moles of helium. So therefore, the total number of moles of all the gases would be equal to 2.10 moles. So therefore, if we were to, let me see here. If we were to basically find the total pressure of the gaseous mixtures by using these numbers along with these numbers, we can basically plug these numbers in, the moles, total moles of the gases, times R times T divided by P, which is divided by V, which is the volume. Then that will give you the total pressure, which is 10.1 atmospheres. In fact, let me do that in this case here. Let me make a little note here that the total number of moles is 2.10 moles. So I'm going to back up a bit here. Oh, wait a minute. I need to record the volume, which is 5.0 liters, and the temperature, which is 20 degrees Celsius. Okay, so let me back up here. So in this particular case, based on the example that I just showed you, all we have to do is put the numbers in. So as far as the number of moles is concerned, that's equal to 2.10 moles times R, which is always 0.0821 liters atmospheres over mole Kelvin times the temperature. Now the temperature is given as 20 degrees Celsius, which we have to convert to Kelvin, which would work out to be equal to 293 Kelvin. And then we divide that by the total volume, which is equal to 5.0 liters. So in terms of the units canceling out, the moles will cancel out, the Kelvin will cancel out here and here, the liters will cancel out here and here, and therefore we can get our final answer expressed in atmospheres. So all we have to do now is to punch the numbers in, times 293, divide by 5. So according to my calculation, this works out to be equal to 10.1, or strictly speaking, the answer should be 10 with a decimal point here because we have two sig figs represented here. So this will be the answer, 10 atmospheres. And if you go back to the slide, which had the example, they have 10.1 atmospheres. So that is basically how we can calculate the total pressure of a gaseous mixture using the ideal gas law. Okay, now let me back up a bit here. To this example, in fact, tell you what, I'm going to stop this video right here. And the next video will be dealing with this particular example. All right? Until next time.